Hi folks, welcome to the Chapter 3 Roundup for Math 621B. Just as a quick disclaimer, this is not an exhaustive list of all the things in Chapter 3, but it's a focus on the important points. You can read the 7 topics we're going to highlight here. The big idea in Chapter 3 is division and being able to factor higher order polynomials. So let's start with some division. We've got two ways, long and synthetic. So if I take this first expression, x to the 4 plus x cubed minus 7x squared minus x plus 6, all divided by x plus 3. The first thing I know is that if I want to do this division, x cannot be equal to negative 3, because we're not allowed to divide by 0. The next thing we'll do is set this up for some long division. So I put the polynomial under the division symbol, and the binomial out front. And here's the process. I have to take x to the 4 and divide it by x. What does that give us? It gives us x cubed. So x to the 4 divided by x was x cubed. Now, I take that x cubed and I multiply it by this whole binomial. X cubed times x plus 3 is going to give us x to the 4th plus 3x cubed. Next step is going to be to subtract all of that off. So I'm going to subtract this. And what will that give me? That will give me no more x to the 4th, so that's good. And I've got x cubed minus 3x cubed, so negative 2x cubed. All right, and I can bring down my minus 7x squared. And I just sort of repeat the same steps. I go to my negative 2x cubed and I divide it by x. Let's see what that gives us. Negative 2x cubed divided by x would give us negative 2x squared. So negative 2x squared goes up here. I take that and I multiply it by this whole binomial. That's going to give me negative 2x cubed minus 6x squared. I subtract the whole thing and keep on going. So subtract all of this. And you have to be careful here. That's minus 7x squared minus negative 6x squared. So this is really like a plus over here. It's going to give us negative x squared. Bring down my next term, minus x. And again, we're going to go negative x squared divided by x. That gives us negative x. Take that negative x, multiply it by the binomial, gives us negative x squared minus 3x. Okay, subtract the whole thing. And we're going to have 2x plus 6. Okay. Divide that 2x by the x, and we get positive 2. And that goes up here. Multiply it by the binomial, and we'll get 2x plus 6. Subtract the whole thing off. And in this case, we end up with a remainder of 0. Okay, so if I were to answer the initial question, what does this become? When I divide it out, I'm going to get whatever I find in here. X cubed minus 2x squared minus x plus 2. Okay, and the restriction was x could not be negative 3. Let's do another one. So in B, I'm going to have the restriction x cannot be positive 2. And I'll set up my division. I'll do it in a different color. Let's go x minus 2 divided by 3x to the 4th. Now, there needs to be a placeholder for every power of x. So we need to also say plus 0x cubed minus 9x squared plus 0x plus 1. Okay, and now we just go through and divide. So 3x to the 4 divided by x, that's going to give us 3x cubed. Multiply it by the binomial, it gives us 3x to the 4th minus 6x cubed subtract the whole thing, and that gives us positive 6x cubed. Bring down this negative 9x squared. Okay, same thing. Divide 6x cubed by x. That'll give us 6x squared. Okay, multiply the binomial through, and we get 6x cubed minus 12x squared. Subtract the whole thing, and it gives us positive 3x squared. And I can bring down that plus 0x. Keep going. 3x squared divided by x is positive 3x. Multiply it by the binomial. You're going to get 3x squared minus 6x. Subtract the whole thing. Gives us 6x plus 1. Okay, 6x divided by x is positive 6. Multiply it by the binomial. That gives us 6x minus 12. Subtract them off, and you're going to get 13. And that 13 is our remainder. Okay? So when we're all done, what that means is that this division is going to give us 3x cubed plus 6x squared plus 3x plus 6 plus whatever's left over. So that is 13 all over x minus 2. Little smartboard issue here. There we go. Plus 13 over x minus 2. And that x minus 2 came from up here. Those are our leftovers. Okay, so that's the basic technique for long division. Now let's see if we can find a shorter way to perform long division. So we're going to do the exact same division over here, but using synthetic division. And there are different ways to set up synthetic division. This is the way I was taught, and it differs a little bit from the Pre-Calc 12 textbook. But when you have x minus 2, here's what you do. You put a 2 out here, a plus, and a times. And those are just reminders. Then you take your polynomial and you write its coefficients in descending power of x. So we have a 3, x to the 4. Remember, we have a 0x cubed. We have a negative 9x squared. We have a 0x. And we have a 1. And here's the process. 3 comes down. Next, we go 2 times 3 and put it up here. So that gives us 6. Okay, and now we add 0 plus 6. Gives us 6. Now we're going to go and multiply 2 times 6. And we put it over here. That's 12. And we add. Negative 9 plus 12 is 3. Again, multiply. And it goes up here. 2 times 3 is 6. And add. Gives us 6. And finally, we're going to have a 12 that goes over here. We add them up, and that's 13. And here's how it works. This last box here, this is your remainder. The powers on each coefficient, they just go down by 1 from this. So you had an x4 to begin with. Now for our answer, we're going to have 3x to the power of 3 plus 6x to the power of 2 plus 3x plus 6 plus the remainder over the binomial. So if you look in the text, that will look a hair different. But hopefully, if we did this right, it gives us the same answer that we got in the last section. Let's see. We did the same division by long division over here. Check it out. Same answer. So either way is fine, but you are responsible for both. Okay, the remainder theorem is a quick little theorem that lets you know what the remainder is going to be when you do a division. It doesn't actually give you the result from the division, but just the remainder. So here's the remainder theorem. If you've got some polynomial, p of x, and it's divided by the binomial x minus a, the remainder is just that polynomial at whatever the a value was. So if you take a look at this one over here, this is actually the division we just did. So we know the remainder should be 13. Let's see if this little theorem works. It says x minus a. So right here it's x minus 2 you're dividing by. So we're going to look at the polynomial at an x value of 2. So all I do is I sub in 2 into the polynomial. 3 times 2 to the 4 minus 9, 2 squared, plus 1. Let's see, that would be 3 times 16 minus 9 times 4 plus 1, or 48 minus 36 plus 1. Holy smokes, it gives us 13. That's great. That's what we found when we did the division over here. The remainder was 13. Okay, and at first this does not seem like it's a particularly useful property, but it will be when we apply it to the factor theorem. So same thing here. If we want to find the remainder in this one, all I have to be careful of is the fact that it's x plus 3 I'm dividing by. And usually we're looking for it in x minus form. So if you see x plus 3, you're going to sub in negative 3. And sometimes the calculator can make your life worse here. I think generally we're better off just doing this in our head. So this would be negative 3 all cubed is negative 27. Minus 2 times negative 3 squared, that's positive 9. Minus 3 minus 4. Or 27 minus 18 minus 3 minus 4. So that should give us a remainder of 2. Okay, just a quick way to check for the remainder. And you can double check your division that way. The factor theorem comes straight out of the remainder theorem. So the big idea is that factors are expressions you can divide a polynomial by, and they leave no remainder. So that means in the remainder theorem, they should give you 0. And that's essentially what the factor theorem is. The binomial x minus a is a factor of some polynomial if and only if p at a is 0. In other words, you get a remainder of 0. So we've got a polynomial over here, and we want to go factor hunting. Well, rather than try and actually do the division, why don't we just check whether we're going to get a remainder of 0. So this first one here is x minus 2. Let's see if it works. That would mean we're looking at the polynomial at 2. That would be 2 to the 4 plus 2 to the power of 3 minus 7, 2 to the power of 2 minus 2 plus 6. And if that's 0, then we get a factor. And if you work this out, we'd have 16 plus 8 minus 28 minus 2 plus 6. This one works out to be 0. Yes, x minus 2 is a factor. Okay, if we were to check x plus 2, then we'd have to throw negative 2 into the polynomial. And it's possible this might work too. Let's find out. Be careful when dealing with negatives. Minus negative 2 plus 6. Okay, that would give us 16 minus 8 minus 7 times 4 plus 2 plus 6. And you can see right away that the negatives outweigh the positives, or if you were to actually work it out, you get negative 12. So x plus 2 is not a factor because we didn't get 0. That's what we want for a factor. X minus 1, so we're looking for p at 1. Checking 1 is really a gift. So anything to the power of 1 to the power of anything is just 1. So this would be 1 plus 1 minus 7 minus 1 plus 6. Hey, what's that going to be? 8 minus 8 is 0. X minus 1 is a factor. Yay! So we have a way to test for factors. Now that we have a way to test for them, let's actually do some factoring. So we know whether a binomial is a factor of p of x, but we don't know which numbers to test for. And this is kind of section 3.3 in your book. It's called the integral root theorem. And here's what it says. If you have a polynomial of this general form, and it has an integer root, that means plus or minus a whole number, or 0. The corresponding binomial factor takes the form x minus a, where a is a numerical factor of k. K is the constant term here. So what it's telling you is test factors of the constant term. If you had some polynomial that was x to the 5 minus 2x cubed plus 37x minus, I don't know, 6, here's what you do. You only test binomials that came from factors of 6. So what's 6 divisible by? Plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now that looks like a lot of things to test, but compared to infinitely many different binomials, it's a big step up. There are only 8 things to test, and you only keep testing until you find one. So let's see that in action. We're actually going to factor a polynomial here. So we find a factor by testing the numerical factors of the constant term. Let's do that. Over here, the possibilities. What can you divide 30 by? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and plus or minus 30. That's a fair number of possibilities. Hopefully we'll find one early on. But here's what we do. We test them now. So let's find out what p at 1 is. It would be 1 minus 4 minus 11 plus 30. Right away, is that going to be 0? It is definitely not. It's 16, no good. Let's try negative 1 then, since that was on the possibility list. That's going to give us negative 1 minus 4 times negative 1 squared, so that's minus 4. 11 times negative 1 is positive 11 plus 30. That doesn't look like it's going to be 0 either, so no good. So all I was doing here is putting the number negative 1 in for x. So let's try another one. Let's try the number 2. Let's find out what happens. 2 cubed minus 4 by 2 squared minus 11 by 2 plus 30. Let me think this through. That's 8 minus 16 minus 22 plus 30. Holy smokes, that's 0. So what have we just found? We've found that x minus 2 is a factor. Because the number 2 worked, x minus 2 is a factor. Okay, and then we get to go and do some division and figure out how exactly to factor this. So x minus 2 is going to divide evenly into that initial polynomial. X cubed minus 4x squared minus 11x plus 30. You can do this by synthetic if you prefer. We've been through how to divide, so I'm just going to do that quickly. Okay, subtract gives us negative 2x squared minus 11x. Keep going, that'll be negative 2x. Gives us negative 2x squared plus 4x. Subtract the whole thing. Negative 15x plus 30. Divide gives us minus 15. And I hope that this will give us a remainder of 0. Otherwise, something's gone terribly, terribly wrong. Phew! Gives us a remainder of 0. Now here's what that tells us. It tells us that that original expression, the cubic, can be written like this. X minus 2 by x squared minus 2x minus 15. Okay? So we've factored out the cubic. That's great. Now we keep factoring if we possibly can. And in this case, we've got a short trinomial. Absolutely we can. We look for numbers that multiply to negative 15, add to negative 2, and there we go. So we found an alternate way of showing this polynomial. And what's good about the way that we found, the factored way, is that it's easier to solve equations from that form, and it's generally easier to graph using your axis intercepts. So the 4 steps, once again: find a factor, divide, rewrite, and repeat if necessary. So if you have a higher power, you may need to repeat. Here's one that we've got. X to the 4 plus x cubed minus 7x squared minus x plus 6. That's the thing that tells us our possibilities. What can you divide 6 by? 1, 2, 3, or 6. Always start with 1. Let's see if 1 works. 1 plus 1 minus 7 minus 1 plus 6. Eureka! Right away we found x minus 1 is a factor. So we divide. X cubed. I'll just do the division. I'll pause it and have it show up. And there's the division. So you could have done that either by long division or by synthetic. But here's what it's telling us. Now we know that that first horrible-looking quartic can be broken up. Unfortunately, we still have to work through and find another factor. Okay, so now we're just going to do the same thing to the cubic. Let's try that polynomial at, well, the things to try would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So I'm trying the polynomial at 1. That would be 1 cubed plus 2 times 1 squared minus 5 times 1 minus 6. I can see right away it's going to be negative. It's not equal to 0. Let's try it at negative 1. That will be negative 1 cubed plus 2 times negative 1 squared minus 5 by negative 1 minus 6. Yep, this one's going to work. Therefore, x plus 1 is a factor. Okay, and now all I'm dividing is this one up here. I need to break it down further. This time I'll go with synthetic division. So x plus 1 is a factor. That means I need a negative 1, a plus, and a times. I need my coefficients from up here. 1, 2, negative 5, and negative 6. And I'm just going to pull them down. Remainder of 0. So here's where we are at this point. We've got that x to the 4 plus x cubed minus 7x squared minus x plus 6. It can be factored like this. We found a factor of x minus 1 to start with. Then we found a factor of x plus 1. And we had leftovers of x squared plus x minus 6. If possible, we'll factor further. So x minus 1, x plus 1, that's a short trinomial. It'll be x plus 3 and x minus 2. Fully factored. And that's our final factored form. Okay, the whole point of this is to be able to graph and solve. So we need to know a little bit about what goes on in the equations of polynomials. So you might have a general form that looks like this. There's a leading coefficient. That's the first number we see. Or if you don't see anything, then it's a 1. We have the highest power, which we call the degree. And we have this k at the end, the constant term. And it determines something in the graph. It tells us what happens if all the x's are 0. Or in other words, what the y-intercept is. It's just what's left when x is 0. Okay, and we have to know something about the basic shape that come out of these. So if you have an odd degree, 3, 5, 7, 9. Remember, degree is just the highest power. If you have a positive leading coefficient, here's the basic look of the graph. It's going to start down. It's going to do a bunch of stuff in the middle. I don't really know what. And it's going to end up going upwards. There's our basic look. Now, I don't know exactly how many turning points there are. We'll have to figure that out. There can't be more turning points than the degree, but we're gonna have to suss it out based on the equation. But it'll definitely start low and end high. If it's an odd degree and it has a negative leading coefficient, it'll just be flipped upside down. It'll start high, some things will happen in the middle, and then it'll go downwards at the end. Even degrees behave a little bit differently. And you know that from parabolas. If they start high, then they end high. If they start low, then they end low. So positive leading coefficients in even degrees look like this. Start from high, and then some stuff happens, and then they go high again. Negative leading coefficients do this. If they're even, they start low, blah, 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 stuff happens, and then they go down again. The last piece of the puzzle is what happens with factored form. So we're doing all this work to factor them. What does factoring tell us in the graphs? It tells us the x-intercepts. So if you have it in the form a x minus q, x minus r, x minus s, these letters are all arbitrary, it doesn't matter. There are x-intercepts at x equals q, at x equals r, at x equals s, and for whatever other factors you have. Whatever's going to make those brackets 0. So let's go ahead and graph. Use n behavior and axis intercepts to sketch the following. Let's think about this. This is odd, and it's got a leading coefficient of 1, so positive leading coefficient. What does that look like? It looks like starting low, blah, stuff happens, I don't know what, and it goes up at the end. That's the general look. The other thing we know is that the y-intercept is at 30. Now, that's not a lot to work with. But earlier on in the presentation, we factored that exact polynomial. So if you go back over here, example 5, it was that polynomial. We factored it. We figured out that it looked like this. X minus 2, x minus 5, x plus 3. So let's use that. And if we hadn't known that, we could just go ahead and find it. So we got y equals x minus 2, x minus 5, x plus 3. It's just another way of writing the same polynomial, telling us that there are x-intercepts at negative 3 coming from this one, positive 2 coming from this one, and positive 5 from this one. Let's sketch the graph. So x-intercepts at negative 3, positive 2, and positive 5. I know in the end it goes up, and it starts from down below. And now I'm just going to connect those. Where's the y-intercept? The y-intercept is at 30. Where's the turning point? We don't exactly know. So that's something that we'll need calculus to figure out. For now, we just do our best with the axis intercepts. And the question says that. Use n behavior and axis intercepts to sketch. So let's try another one. This is the other one that we had factored. So again, it's got a positive leading coefficient. And this one is even. So it has the basic shape. Stuff happens in the middle, but up to up. It has a y-intercept of 6. We factored it earlier. I think this would have been example 6. And here's what we got. X minus 1, x plus 1, x plus 3, x minus 2. Okay, that's telling us that we have x-intercepts at 1, -1, -3, and 2. Let's go ahead and graph them. X-intercept at -3, -1, at 1, and at 2. I know that it goes up to the left, and it goes up to the right. And now I'm just going to connect with a smooth curve all those x-intercepts. I don't know how far up or down the turning points go or exactly where they are. I do know that the y-intercept here is 6. Okay. So that's all the basic information that we can graph easily. We're going to take a quick look at the multiplicity of roots, because any powers that are on those x-intercepts actually change the look. So you can see here that I've got this graph that looks kind of funny. Sometimes factors are repeated, or they're raised to powers on a polynomial. The degree on the repeated root, tells us what is happening on the graph at each x-intercept. So look at this one here. Over here we have just a regular factor of 0. And look on the graph, we just have something regular going on there. It goes straight through the x-axis. Now let's look at the next one. X plus 1. That's an x-intercept at -1. Ooh, this was an x-intercept, but it was also a turning point. Okay, this one over here, this would be at 1. Let's see what happens there. Well, there's a funny sort of, it's going down, it's going to turn around, it's going to turn around, and then it decides to go through anyways. It's like a hesitation. Let's just call that Okay, let's check out what happens at 2. X minus 2, we get another turning point. X minus 3, we get another Here's what's going on. When you have roots that are raised to even powers, you get turning points. Okay? So notice here and here we had turning points. And those turning points either look like this or they look like this. But they're on the x-axis. So when we say roots, we mean x-intercepts. Roots that are raised to odd powers are what we might call hesitations, or technically they're called changes in concavity. So they look like going up, maybe turn around, but no, decide to keep going. Or if they're coming from the negative, going downwards rather, they look like this. Okay? They look kind of like your most basic cubic graph. Anytime you have an odd power, that's going to take place on a root. So let's do a sketch using that. First of all, we've got a leading coefficient that's negative. Let's check out the power. You've got an x to the 3 here times an x to the 2 times a regular x. That means degree 6 or even. So negative and even looks like this. Stuff happens. But it goes from down to down. Okay. In terms of finding the y-intercept, if it's in factored form already, you just sub in 0 for x. So that'll give us 0 plus 3 all cubed, 0 minus 1 squared, and 0 minus 4. And then we just work that out. And when we do, we're going to get the number 324. Seems like a big number, but that's okay. We're just going to mark it as 324 on the graph. It doesn't make it any harder. Now, let's see. Our x-intercepts. We have one at -3, and it's an odd power. So that is a hesitation, or a change in concavity. Okay, so hesitation is not a real term for it, but it's a good way to remember it. We have one at 1. That's got an even power, so it's a turning point. And we have one at 4 that is just regular. Okay, let's set it up. 1, 2, 3 in the negative. 1, 2, 3, 4. I know that it's got to have this x-intercept, this one, and this one. I know that in the long run it goes down. Now let's make sure I'm going to come at it properly. That first one is a hesitation. So it comes from below and it hesitates, but then it pulls through. Okay. Now I have to get myself over to the next turning point, or to the next x-intercept rather, which happens to be a turning point. Now I have to get myself through that very last one, which is just regular. So I've shown my hesitation, my turning point, and finally I'm going to show that this is 324. Last thing we'll take a quick look at is solving higher order equations by factoring. Really, if you can do the graphs, these should be a breeze. So to solve by factoring, it's the same as quadratics. You set it in equals 0 form, you factor your expression completely, and then you solve the elementary equations. So over here I've got this, which doesn't look great. Let's put it in equals 0 form. So I need to move this over by subtracting 4x squared. I'll put it in descending powers of x. I need to move this over by adding 30. And we're just going to take advantage of the fact that we have factored this one already in the presentation. And if you want, you can go back and check that out, how it looks. But by hunting down a factor and then through long division, we came up with this. That's an easy equation to solve. As long as one of the brackets is 0, then the whole expression is going to be balanced, or the whole equation will be balanced. So if x minus 2 is 0, or if x equals 2, then we've got a solution. If x minus 5 is 0, or if x equals 5, we've got a solution. And finally, if x plus 3 is 0, or x equals negative 3, then we've got a solution. And there are 3 solutions. You could check them in the original one. And let's just do that for x equals 2. Check x equals 2. The left side would be 2 cubed minus 11 times 2. The right side would be 4 times 2 squared minus 30. Let's see what we get. That's 8 minus 22. This is going to be 16 minus 30. On this side, we're going to have negative 14. This side, we have negative 14. Yay, x plus 2 is a solution. We don't really need to check. These are all going to work out as long as it says they're solutions, unlike the radical equations. All right, I hope this has been a good refresher on the concepts in Chapter 3, and good luck.